All right. Hi, everyone. Thank you so much for having me. It's just such a privilege being here with my Keck family celebrating 30 years of what is my favorite telescope in the world. Easy to say when other telescopes are in space. But today, what I'd like to celebrate with you is the Kepler Giant Planet Search 1, which is the name that my collaborators and I have given to a decade of Kepler planet host radial velocities that we've collected from the W.M. Keck Observatory. So, as with any research that happens over a decade, this is really thanks to a large number of people in the community over the past decade. So thank you all so much for being part of this project. All right, so to understand the science of the project, let's start somewhere familiar, our own solar system. The giant planets played an important role in planet formation here. In particular, Jupiter and Saturn were responsible for keeping our terrestrial planets small. And Jupiter might have directed water-bearing comets toward Earth, influencing or perhaps even causing the origin of life here. From Doppler surveys, also conducted at Keck Observatory, we know that roughly 15% of Sun-like stars host Jupiter-like planets. But what is not yet well understood is whether giant exoplanets help or hinder the growth of Earth-like exoplanets. Although the NASA Kepler mission discovered thousands of planets between the sizes of Mars and Neptune within 1 AU of their host stars, the mission was practically blind to Jupiter analogs. And this is because planets at the orbital distance of Jupiter have only a 0.1% chance of transiting their star. And for them to transit is a prerequisite for their detection with a transit mission like the NASA Kepler mission. Also, the duration of the primary Kepler mission was only 4 years, which is quite short compared to the orbital period of Jupiter, 12 years. So at most, a Jupiter analog would transit once in the Kepler data if you got really, really lucky. So how did we go about finding the Jupiter analogs? Well, fortunately, as John alluded to earlier, we have other methods for discovering Jupiter analogs. And in particular, the radial velocity technique shines at this task. My colleagues and I have spent literally the past decade, since I started as a grad student at UC Berkeley in 2011, gathering precision radial velocities of Kepler's planet-hosting stars to measure the transiting planet masses and also to search for whatever Jovian companions to those planetary systems we could find. In this paper, the Kepler Giant Planet Search 1, we present the radial velocities that we gathered as part of this survey, 2,858 RVs over the course of a decade, as well as the planet properties and planets discovered. And this is just the first of a series of papers. So this is just our RVs here. Future papers include looking at the occurrence of Jovian companions to small transiting planets and additional patterns. I've actually got multiple students and postdocs working toward this, and I want to give a shout out to my postdoc, Dr. Matthias He. He and I co-authored a paper called Inner System Gap Complexity as a Predictor of Outer Giant Planets. So if your dream in life is to go find giant planets to systems with small planets, we can point you to which ones you should spend your precious Keck time looking at. All right, so the stars that we selected are Kepler planet-hosting main sequence stars that are actually quite comparable to the field stars used for blind RV surveys. The figure on the left is showing the stellar temperatures and radii for the stars in our survey compared to a 30-year-long Doppler California Legacy Survey, also conducted at Keck, that was recently published in Rosenthal et al. 2021. And the figure on the right shows the cumulative distribution of the host star metallicities. So the point to take away here is that these Kepler planet-hosting stars really had very similar properties to the field stars around the sun, places where we might look for Earth 2.0 with the Habitable Worlds Observatory. They, like the sun, are a bit more metal-rich than the typical star in the galaxy, shown in the green distribution from Ragavan et al. But these are the stars where we've classically, over the last 30 years, been looking for planets. Now we've turned our attention to stars where we actually know they're small planets, and we are looking for Jupiters. For each of the 63 stars in the survey, we've reported the number of transiting planets, the number of sub-Saturn giant stellar non-transiting companions, the number of RVs we collected, our observational baseline in years. Maybe for the next version of this paper, I'll do it in decades. And the RMS of the RVs, and actually nicely an upper limit on M sin I of any companions at 10 AU. So we're now probing the outer reaches of planetary systems in orbits comparable to Jupiter and even Saturn. We also report the physical properties for both the transiting planets and the non-transiting companions, many of which are shown here. So let's spend the rest of my talk looking at a few of my favorite systems. This system, Kepler-68, has 2 transiting sub-Neptune-sized planets, and we detected Jovian companions at 1.5 AU and 5.3 AU. The radial velocity time series spans from 2010 to 2022, is shown on the left, with the best fit model shown in blue. And the 4 panels on the right show the RVs phase-folded to each of the planets in our model. We've got the 2 cute little transiting planets up here near a 2-to-1 mean motion resonance. A Jovian planet at 623 days, that's the one at 1.5 AU. It was previously known, but we've updated the orbital period, mass, and eccentricity, and we present a newly discovered Jovian planet. Look at that period, almost 5,000 days, an orbit of 5 AU. Jupiter orbits the sun at 5 AU. So we're finally truly sensitive to Jupiter analogs. This is actually just half a Jupiter mass. This system, Kepler-139, illustrates the story of why we're not allowed to give up looking for giant planets. It really shows the risk of what happens when we stop. So this system has 3 transiting sub-Neptune-sized planets, and here we actually did discover a Jovian companion at 3 AU, but we almost didn't discover it. So here's why. The first 3 RVs we took, there's actually 2 of them up here, and then a few years later we came back and took another RV. They were all near the up quadrature of the Jovian. We didn't see any RV variation in those first 3 RVs over multiple years. It was only with the 4th RV that we realized, oh goodness, something's happened. There's a giant planet here. And so that was when our efforts intensified and we actually detected this beautiful RV signal from a giant planet. So here's the radial velocities phase-folded to the orbit of our newly discovered Jovian companion at 3 AU. This is another system I love, Kepler-407. This has a transiting ultra-short period, so period of less than 1 day. It goes around the star, rocky planet. It's only 1.5 times the size of Earth. And this tiny little hot rock has a Jovian companion at 3.3 AU. At the time this system was announced back in 2014, as indicated by the pink arrow, the giant planet was only seen as a trend since a full orbital period had not passed. But now we have sampled 2 full orbits of this giant planet, and we have greatly refined its orbital properties. It is a massive Jovian, nearly a brown dwarf, and it has a significant eccentricity, and it's at 3.3 AU. And interestingly, this non-transiting companion is a factor of 2,000 more massive than the rocky planet. So this is telling us something wonderful about how planets form. I think our most dramatic discovery was not actually a planet, but a stellar mass companion to a system of 4 transiting planets. The transiting planets are all Earth-sized and are all interior to 0.1 AU. They're actually not even shown here because their RVs are result in non-detections. But over the last few years, we saw the star approach periastron producing a change in the RVs of several kilometers per second. This distinctive non-sinusoidal shape of the RV time series allowed a very precise determination of the companion's mass and eccentricity. It is 200 Jupiter masses and highly eccentric at 0.66 eccentricity, not quite as eccentric as Andrea Gheza's favorite stars around Sagittarius A star, but this, in planet world, this is quite impressive. What this means is that the periastron passage distance of this star is just 4 AU. And remember, there's a whole bunch of cute little Earth-sized planets interior to 0.1 AU. So this configuration indicates that the star likely truncated the protoplanetary disk, and possibly in a manner that stunted the growth of the little planets, keeping them little and cute and Earth-sized. So it might be that an eccentric star has helped form rocky planets. Here are the architectures of the 63 stars in our survey. The semi-major axis is shown vertically. I've turned it sideways so that you can all see it. And the different system names are actually up here off the top of the figure. And they're just ranked by the semi-major axis of the innermost planet, producing this lovely pattern here. The point sizes correspond to the square root of the planet's mass, or m sin I, and color corresponds to eccentricity, with the most eccentric companions colored bright yellow. Here they are, they're actually stars, not planets. The red triangles, here, 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 indicate radial velocity trends we detected that have not yet inflected in our decade of observation. But if they're bound orbits, which they should be, at some point they will turn over. So this just tells us there is more work yet to be done in probing the architectures of these planetary systems. We can place these points and their companions on a plot of planet mass versus orbital distance. And systems that contain a Jovian mass or larger body are shown in color, corresponding to the most massive companion in the system. And what I really want to drive home here is this survey spans 7 orders of magnitude in planet mass, from Mars-sized bodies to stars, and 4 orders of magnitude in orbital distance. In summary, I've spent the last decade of my life with the Keck Observatory leading this Kepler giant planet search, with much help from many patient co-Is. We've obtained 2,858 radial velocities of 63 Kepler systems that have transiting sub-Neptune-sized planets. We've characterized 185 planets in total, including 26 non-transiting companions, which include 13 Jovian planets, 7 sub-Saturns, 3 stars, and 3 ambiguous trends. We have also updated the masses of 84 transiting planets, and this, along with a wonderful paper from our collaborator, competitor, frenemies on the HARPS North team, is the longest running and most data-rich collection of RVs of the NASA Kepler systems yet. So I'm just so proud of what we've accomplished with 1 decade at Keck, and I'm very excited to see what the next decade of exoplanet dynamics at Keck will bring. Mahalo.